Hello, students. This is Dr. Faizan Mirza. In this video, I'm discussing a question that deals with an example of cat and how could there be a cat with and without tail in each gender, be it male or female. And they have added a chi-squared calculation with this as well. So this is kind of a different type of question that came in October, November 2011, variable 53. Again, I would just recommend that once you are done with this video, do try to attempt this question all by yourself and see where you get stuck. So coming back, question two. So this is question two, and the question actually tells you about a variety of domestic cat does not have a tail. This condition is controlled by a single gene with two alleles. These alleles are with the tail and without tail. We do not know which one is dominant, which one is recessive, because all this working I have done by decoding this table 2.1. So we do not know which one is dominant and which one is recessive. We are just told that the cat could either be with tail or without tail. Table 2.1 show the results of the four crosses between there are four crosses between cats with tail and cats without tails. Each male was crossed with several females. Each male was crossed. We know the males have XY chromosome both, and the females have XX chromosomes. So we know if it's a sex linked trait, the phenotype ratio would be very different because the males receive Y chromosome from the father and X chromosome from the mother. So they have just one copy of X chromosome as compared to females who have two chromosomes, which are X. So coming back, parental phenotype cross 1, cross 2, cross 3, cross 4 shown to you, male and female, offspring phenotype, male and female, with tail, without tail, with tail, without tail shown to you. Let's come to cross 1. Cross 1 shows without tail being crossed, and the organisms which are produced are male and female both. With tail, without tail, both kind of males are produced. Similarly, females with tail and without tail, again, both are produced. So we have four different phenotypes and two in each of the gender. In the second, we are having with tail and with tail, we are crossing them together, and we are only having with tail males and with tail females. Anyone who's without tail is just not produced. It means all 100% offsprings in this cross 2 are with tail. Now, how do we know that this with tail could be the recessive trait here? Because when you cross a small t, small t, small t, small t together, all 100% offspring will be small t, small t. So if you try to cross it, just try to cross this small t together. So all 100% offspring will not be carrying the tail, will actually be carrying the tail. They won't be without tail. Okay. How do we know that without tail might be dominant? So the first cross shows to you that we had two cats and they both were without tail, and you cross them and you got four phenotypes here. Four phenotypes. So for example, if both of these or any one of these was homozygous dominant and the other was heterozygous dominant, we would have received all the cats which actually were having the capital T allele, and the capital T allele is for without tail. So all 100% should have been without tail. We do not have this. We have cats having the tail as well. So this shows to you that both of these are hybrids. Both these parents are heterozygous. So they must be capital T, small t, capital T, small t, because only in that case we have this kind of a ratio going in which you cross two hybrids together, you get 1:2:1 phenotype. And this is, we are seeing four different phenotypes here. So this is the, again, with tail and without tail, and with tail male and females are being crossed. One is with tail, the other is without tail, then one is without tail, the other is with tail. And again, the ratios, you are seeing four different phenotypes in each. Again, you see in this third cross, you took the male which is having the tail and female which is not having the tail. Males which are produced are 40:25. If you try to take this ratio and round it off, this somehow comes closer to 1:1. Similarly, 25 to 36 with tail and without tail female, this also comes out to be almost 1:1. Genetic ratios are almost always rounded off. They are not exact 1:1. They are never 3:1 or 1:2:1 precisely. They all get rounded off to the nearest whole number. Similarly, without tail and with tail, if you try to cross them together, again 35 and 27, they are again in the similar 1:1 ratio, and 38, 36, again they are in similar 1:1 ratio. So these two crosses show to you that this cannot be a sex-linked trait. If this was a sex-linked trait, then one gender would be missing onto one of the phenotypes altogether. Now, if we start with this question, so my most probable outcome of all these crosses is that the first cross is between two heterozygous, the second cross is between homozygous recessive both, the third is between one homozygous recessive and the other is homozygous heterozygous dominant, and the fourth is the other is the heterozygous dominant, the first one is the other one is the homozygous recessive. So coming back, explain how the results of cross 1 and cross 2 show the alleles without tail is dominant. Already we have discussed that in cross 1 without tail, cat is dominant. Cross together, offspring produce that have tail. So organisms with tails are being produced. That means they both were the carriers of the recessive trait. Because if they both were the carriers of the recessive trait, only then the recessive trait can be seen in the offspring. Cross 2 with tails crossed together, no offspring without tail, 100% offspring carrying the recessive trait, because this is exactly when you cross recessives together, all 100% offspring carry the recessive trait. The dominant cannot show because the dominant allele is just not there in the parent. Explain how the results of cross 3 and cross 4 show that the genes of this condition are not sex-linked. Already discussed with you that 4 different phenotypes can be seen and they are all in the ratio 1:1 in each gender. So both these actually show to you. Plus, if it was a sex-linked, so males would all be tailed. So if this is not the case, we have males which have tail and we have males without tails as well. So this shows to you that this is not sex-linked. Based on the results of cross 1 in table 2.1, a student conclude that cats without tails are always heterozygous. Okay, maybe. The ratio of the offspring with tails without tails is not expected as that of this type of a cross. Why? Because if we go back to the first cross, if one of them was dominant, the other one was a carrier of the recessive trait, all 100% offspring should have the capital T allele, which means without tail. So only without tail should have been produced in this first cross. There should have been 0 in these columns. This should have been 0. This should have been 0. But this is not the case. Without tail are being produced together with tail. So coming back, this is what he or she, the student, say the cats without tail are always heterozygous. Now moving on, the ratio of these offspring with tails and without tails is not as expected for this type of cross. Okay, so he or she is probably saying it's not like 1:2:1 or 3:1. The student carried out a chi-square test to determine the offspring ratio in cross 1 differed significantly from the expected cross between two heterozygotes. State one reason why the student chose this statistical test. We know the discontinuous data observed and expected being compared. We use chi-square test. So if we start to come to the calculation part of this particular cross. Now, since it's a chi-square test question, it needs extensive practice. It needs the proper understanding of the ratios, that which ratios should be expected where, because all the expected calculations from the offspring are taken out from the ratio that we know that can happen in that cross, and observed is the value provided to you. So here the complete table 2.2 shows the chi-square for the results of cross 1. Cross 1 was both were the carriers of the recessive trait, and we had 4 different phenotypes. So offspring phenotype observed were 40, offspring with tail and offspring without tail were 72. If you can just add them at the back, you can get this. Okay. Expected. How do you get the expected here? So the total number of offspring is 40 plus 72. So if you add 40 and 72 together, we get 112. So there are total of 112 offsprings in this case. 112 offspring should be 3 by 4 into 12, which is total, and 1 by 4 into 112, which gives you 84 and 28 respectively. So we mentioned these here. Why 3 out of 4 and 1 out of 4? Because we know that if it was a case of both heterozygous being crossed together, which apparently is this case because we have offsprings and these with tail ones are not 0 here. So if you cross them, we get 4 different phenotypes. We have capital D, capital D, capital D, small t, capital D, small t, small t, small t, and the phenotypic ratio is 3:1. So using the 3:1 ratio, we are using this ratio of 3 upon 4 into the total and 1 upon 4 into the total, and having these expected values. Once the observed and expected are there, we just go and subtract the O minus E values. This is the O40 and this is the E28. You subtract these, you get the answer O minus E. Then O minus E is squared further. So I get 144 here. I'll divide this 144 with the expected value of 28, because O minus E squared over E represents that this value, which is the square of O minus E squared must be divided by the value of E. So my answer comes out to be 5.14. Similarly, for the second row, I have 72 and 84. I'll subtract them and I get minus 12. If I square it, I get 144. And if I divide it by its expected value, which is 84, I get 1.71. Now, all these values of the last column are always taken at two decimal places. Now, what we'll do, we'll add these together to get the chi-squared value. It comes out to be 6.85. Table 2.3 shows some critical value of chi-squared at different probability levels. We know we always pick on 0.05 probability level, which means we are 95% confidence and we are leaving 1 in 20 chance of error. How many degree of freedom will you pick? Now we know there are two categories here. So n minus 1, which is number of categories minus 1 for chi-squared test, will give you 1. So we'll pick up the degree of freedom 1. So this is actually what's asked here. State why the student should look for the critical value at 1 degree of freedom in the specification, because the degree of freedom n minus 1, the number of categories is 2. So 2 minus 1 comes out to be 1. State the conclusion from the chi-squared value. So if we go for the degree of freedom 1 and the probability level 0.05, we get the critical value of 3.84. Our chi-squared value is 6.85. So if we compare the chi-squared value with the critical value, we know that the chi-squared value is greater than the critical value. So whenever the chi-squared value is greater than the critical value, the difference is not due to chance and it is due to some other factor. And that some other factor actually tells you that there is something going on and the offsprings are not being produced in the 3:1 ratio. This ratio is missing. Something is just not going the way it should. It's beyond what we are expecting. So what further on the student did? Eventually, it was concluded in the study, obviously with some other experiments. Cats without tails are always heterozygous for this gene. Homozygous dominant cats are never born. Suggest what could account for the effect of dominant allele in the homozygous condition. So if capital T, capital T were present together, what outcome would it have? Why is it not being produced? Why are they saying they are never born? You need to recall the lethal gene combination. The lethal gene combination, whenever the lethal gene combination comes about, the zygote stops dividing. The zygote will not be formed, the embryo will stop dividing, the cell division will just not take place. It's a lethal gene combination. This is something similar to what we have discussed in hemophilia, that we do not have females who suffer from hemophilia, the hemophilia that we have discussed for factor 8. Why? Because this is a lethal gene combination. So whenever there's a lethal gene combination, two alleles coming together, could be recessive, could be dominant. If they are never produced, if they are never seen in that phenotype, it just means that this is a lethal combination. And this is exactly why this particular ratio is not coming 3:1, and it's coming to be something very different. And we have proven this with the chi-square. This was a very tricky question and probably among the tricky most questions that I have seen for chi-square test. I would recommend that you go and pick up this question and try to attempt it yourself. And let me know if this video was helpful for you. That's it from my side. Thank you so much.